With that, I am pleased to introduce Dr. Umberto Saetti. He will be joining us June 1st, and we're already trying to order some equipment to get sort of address that very question, Scott, and we're excited to have him join us and see how he fits in. So Umberto, the floor is yours.
Thank you, Dr. Thoreau. Hello, everybody. Thank you for being here. What's my presentation? Hold on just one second. I lost my cursor. There you go. Okay. So, all right. So, hoping that I'm sharing the right screen. My presentation will talk about the intended networked flight simulation and control laboratory that I plan on establishing at Auburn, and for which I'm already starting to order some of the equipment. I will start with an introduction. First, I'd like to present myself. I graduated from Penn State with my PhD in 2019. And I also got my master's there. Prior to that, I got my bachelor's from Polytechnic University of Milan in Italy. I am currently finishing my postdoc at Georgia Tech, but as Dr. Thoreau said, I will be joining Auburn June 1st, so pretty soon. And before that, I was a Penn State graduate research assistant, and I also had the opportunity to spend some time at NASA Ames working for the U.S. Army Aviation Development Director. And my research field is mostly flight dynamics and controls, system identification, and time periodic systems. Applications span rotorcraft, especially helicopters, some eVTOLs, and also unmanned aerial systems, flapping wing flight, so insects and birds. That's something I took on more recently, and also some fixed wing aircraft. So, as a background to network simulations, well, simulation networking started back in the 1980s, even late 70s. And two examples of the earliest simulation networking systems were the DARPA SimNet and Multisim, as articulated in the studies by Miller and Thorpe and George Lowell. And typically, these kind of systems were used for either a mission rehearsal or team training in military operations. And some of the advantages of these systems were that linked simulators are heterogeneous, so they can simulate either aircraft, helicopters, or different vehicles in general. The simulation units do not need to be collocated. In fact, distributed simulation units can be connected across large distances to the same simulation environment. And also, these simulations are flexible in the sense that simulation units can be added and removed without disruption to the main system. So this kind of architecture allows for multi-pilot or multi-aircraft operations, such as aerial refueling, cooperative land load, carriage, air combat, or air traffic management. There may be also other examples. However, these systems have been historically not used in general for research. So how can we take these ideas and make them more contemporary? And so one thing we can do is to start observing that some of the past approaches used projected screens and large motion bases and realistic physical cockpits, just because there was no other way to model a cockpit of an airplane, if not physically. So this contributed to making the system very large and heavy, and therefore made them have a high acquisition, maintenance, and operation costs. So typically, this kind of network systems were government initiatives rather than university initiatives, just because of the cost associated to them. So, however, the advent of virtual reality can significantly change things in that it eliminates the need for large projected screens and physical cockpits, which reduces the size and weight carried by the motion platform and of the motion platform itself. So this allows for a lower mass of an inertia over the motion platform, and so increased bandwidth, motion, and range. And also, it allows for a lower cost, and so more And so this kind of network simulations become more affordable also for academic research and only for government or for large corporations. And also, one could think about virtual reality, it is that it allows for a 360 visual environment, rather than a visual environment that is limited to how big the projected screen is. So moving on to the laboratory vision, so the approach that I would like to take is for the Plan Lab is to merge the latest technologies in virtual reality and augmented reality, the latest technologies in motion tracking and haptic feedback pilot suits as well, with a motion-based simulation unit that you can see there on the right to allow for immersive augmented reality simulations suitable for research purposes, with the platform that is contained in size and also in cost. And so in addition, I plan on linking multiple of these units for starters, 2 of them, and then I may acquire more in the future. And so to allow for research that involves multiple pilots or aircrafts, such as, again, aerial refueling, cooperative slang load, carriage, air combat, or air traffic management, and there may be other applications as well. So the resulting system that I plan on building would be therefore multi-purpose in that it can interface with multiple simulation environments such as MATLAB, FlightLab, or Julia. Can simulate different cockpit graphics, because within the graphical interface that we'll use for at the beginning at least, which is X-Plane, one can simulate or construct different simulation cockpits. The system will be reconfigurable because it will be equipped with both fixed wing and rotorcraft controls. So the system will be able to simulate either general aviation airplanes, jets, but also rotorcraft, and also it will be able to we'll be able to implement motion queuing systems, different motion queuing algorithms. It will be modular in that multiple units will be able to be linked together, and it will have some kind of an enhanced motion queuing experience, just because the weight on the motion platform is basically just that of the pilot, and so it has pretty low mass inertia that gives an increased motion bandwidth and range, and we'll see some of the characteristics of the simulator later on in the presentation. Also, the simulation will be immersive because virtual reality provides a 360-degree vision environment, and it allows for a look-down capability, which is very important for helicopters, but that many simulations out there do not have, just because they're not using virtual reality. So that's one of the perks. Then there are also, of course, also downsides of using virtual reality. Another perk is that the augmented reality approach, which is basically a feed-through approach for the pilot, in the sense that the pilot can see the simulation environment, but can also see outside of the simulation. And so the pilot will be able to see its hands. And if not with this approach, we'll be able to, through the pilot suit, build a projection of the pilot hands in the simulation environment so that the pilot can actually see its hands and interact with the physical objects in the cockpit. So also the simulation will be immersive in the sense that they will use haptic feedback. So haptic feedback will be provided to the pilot both through force feed controls, through a full body haptic feedback suit, and through the haptic feedback gloves. So this system will enable the following broad research topics. So the plan will be to conduct fundamental research on virtual reality and augmented reality for piloted flight simulation and handling qualities evaluations, development and testing of advanced flight control systems, novel queuing systems and algorithms such as tactile queuing systems and haptic force field, the haptic cueing system through the suit and through the controls. For one example is that the position of an adversary fighter jet would be cued to the pilot body through the pilot suit. So the pilot would feel the position of the other aircraft on its body. So that's one of the ideas that it's actually been researched in the past. That's why I'm able to speak about it. Also, another avenue for research will be simulation of high acceleration flight with a low acceleration motion feedback, because of course the motion system that we have has some limitations in the accelerations that it can provide. However, with the pilot suit, one can simulate the accelerations on the body of the pilot with localized pressure. So that's another thing that could be studied. We're going to study human-machine interaction and also development of pilot models. So just to give a brief rundown of the main highlights of the equipment. So about the motion base and the virtual reality headset, the motion platform is about 600 pounds, equivalent to 300 kilograms. And the displacement, especially of the angular motion, it's about 30 degrees, but it has a pretty high bandwidth in that it arrives at about 120 degrees per second, which is high compared to other motion platforms out there for the same cost. And the visual system, it's a VR Engineers X-Style 8K, which is, for now, at least the most advanced headset available on the market. The resolution is about 5K per eye. And it's got about a 180 degrees of field of view and pretty high refresh rate. It also has hand tracking, so it can track the hands of the pilot and recreate them in the simulation environment through the UltraLeap technology. And it also has eye tracking for in case one wanted to study human factors as well. About the haptic feedback pilot suit, this is a Tesla suit, and it's got a haptic feedback system with about 80 electrostimulation channels and 114 electrodes. It has the capability of biometry and also motion tracking through both 6-axis and 9-axis IMU. The 3 additional axes there from the magnetometer, and it transmits its data through Wi-Fi. And then the last piece of equipment that I plan on acquiring and using are feedback gloves, so that a pilot can be cued information and with these haptic feedback gloves. Of course, the simulation units would be nothing without a brain to power them. So during my postdoc, I took some time to develop several simulation models, one of which is called Rotorcraft Simulation Engine, or ROSE, as it started as a simulation environment for rotorcraft. However, it also became a simulation environment for aircraft, so I will have to change the name soon. In any case, this simulation environment is developed both in Julia, which is a programming language by MIT, open source and compiled, which is similar to MATLAB, but not exactly the same, because Julia is compiled, MATLAB is interpreted, so different approach, but similar results. And also the simulation platform is also available in MATLAB. I have different various fidelity models for helicopters. I have a simple helicopter model based on the the theory in the PAD field book. I currently have UH-60, Bell 430, and other helicopters available in that. A ARM-COP model, which is based on a NASA technical report, which is a little bit higher fidelity, but not significantly. GenHel, which is a simulation model that is typically used by Sikorsky, but is available through a NASA technical memorandum, and it's higher fidelity, but I would say mid fidelity. But I recently augmented it with a state space implementation of a free wake, so CFD for the rotor, and which has thousands of states. So this is very high accuracy. I also have other models available, models for an F-16, so fixed wing aircraft. And also I recently developed an air acoustic solver for solving for the noise produced aerodynamically by a helicopter. And this is based on a marching cubes algorithm, which is typically an algorithm or strategy that is used in computer graphics because it's pretty fast. Also, the graphics that will be used by simulator is explained. So simulations could be, the configuration of the simulators could be rotorcraft, fixed wing, or fixed wing, depending on the mission task that we need to accomplish. I will go very briefly through the intended research that I plan on using the simulators for. One of which is the linearization linearization of the coupled flight dynamics and acoustics of a rotorcraft. For doing so, we can use the Fox-Williams-Hawkins equation, which describes the aerodynamically induced noise. Through the coupling of some of the simulation models that I described before, one can include the noise as an output of a dynamic system of a rotorcraft, and then linearize through linearization methods that we're developing, and therefore can use these linear models to then control the noise of the helicopter and try to reduce it. And so this can be applied for both noise in communities or noise in the aircraft, so cockpit noise. And then queuing methods can be developed through the simulation units that I described to queue perhaps the noise to the pilot and see and make the pilot aware of the noise that the aircraft is producing on a particular point on the ground or in the cockpit or somewhere else. Other research that I plan on that I've already started doing, but I plan on continuing, is the application of neural ordinary differential equations to aerospace vehicles. Recently, neural networks have been formulated as ordinary differential equations. And so I plan on trying using these mathematical constructs as an alternative to system identification, and use the simulation units to provide the data for system identification. And then a bunch of other topics on identification of time periodic systems of novel helicopters, control system design for pilot queuing for out rotations, and some dynamics and control on eVTOL vehicles, similar to what Dr. Chakraborty does. There could be very many opportunities for collaborations here. And also, one thing the simulation units will not be used for, but is the study of the stability and control of biological and bio-inspired vehicles, such as insects or flapping wing microaerial vehicles. All right, so this is all. I thank you for listening, and I'd be happy to take any questions you may have.
I have a couple of questions. One really cool. I didn't understand what the Heptic outfit, what is it? What are you using it for?
Right. So, for example, one of the ideas, one of the ideas that I have, for example, could be is that one could queue, for example, the location of some other aircraft that the pilot may be the pilot could use sorry, I'll start over. One could queue the position of another aircraft, which may be adversary or an enemy or not, of the pilot on the body of the pilot through localized pressures, in order for the pilot to know where this aircraft is for whatever reason, for escaping from it or for chasing it down. Another way of using haptic feedback could be to let the pilot know if any envelope limit of the aircraft is being reached. So, for example, if the helicopter is in a position where rotor loads are getting too high, then one could use haptic feedback either through the suit or through the controls to let the pilot know that he's exceeding some flight envelope limits. So this could be some of the ideas.
I think. So the other thing is, I thought Julia is a language, and you were mixing it with MATLAB, which I thought was a platform. And so, are they programming? Are you programming in Julia, or am I misunderstanding what you were implying by that?
Yes, I am indeed programming in Julia. I have the simulators that I developed. They're available both in MATLAB and in Julia, but separately. Yeah. But I plan on going open source with the Julia version, probably within the next year or so.
But Julia is the MIT developed, but it's just a language that can be used by anybody.
Indeed, yes.
Yeah, thank you.
Yes.
Dr. Cietti, quick question. How long would it take you to add another aircraft to your simulation, such as the Air Force TX?
So I currently have capabilities of adding rotorcrafts quite easily through the simpler model, just because it doesn't require many parameters to be set up. However, for fixed wing aircraft, my model is for the F-16. The model is based on the Stevenson Lewis book, which has all the parameters for the F-16 and all the lookup tables. So in order to develop something like that for another aircraft, I would need all the necessary lookup tables. If those are available, then we can develop a simulation model quite, I would say, it would be feasible in a relatively short time.
So you're talking about the data package basically on the airplane.
Exactly.
Okay, very good. I'd like to talk to you maybe offline about this a little bit.
For sure, that'd be great.
Hey, Scott, me too. You and I are kind of in the same field of work. Dr. Cietti, one question with the haptic suit. Are you able to simulate to a certain degree, especially if you were getting into the TX, which I guess they call them the T7 now, F-16, the Viper? Is that haptic suit able to also simulate I know you probably can't to a full degree, but simulate G-forces, for example? That's one thing that as a former Air Force pilot, we really miss out on in simulator training is the G-forces that you experience in the aircraft versus in the simulator. You just don't, at least not now. But is that haptic suit able to simulate that to a degree?
That's right. Yes, that's precisely the idea. I would plan on trying and simulate some of or recreate the G-forces through localized pressure. Now, the Tesla suit is not a pneumatic suit, so it doesn't have. Well, let's say that the localized pressure that one can provide is limited, but it's feasible. So that would be one of the first things I would like to try and do.
Okay.
And Dr. Cietti, one other question on the haptic gloves. One of the limitations on VR, as opposed to the augmented reality, is the pilot reaching over to throw a switch or to move a dial or whatever. With those haptic gloves, can you simulate that feel, basically?
Yes, that's exactly the idea. So there are two approaches to that. So one would be either to have the VR goggles, use the cameras from the VR goggles to blend the video of the outside reality to the graphics reality, and so that the pilot can actually interact physically with the cockpit that may be physically present on the simulator. The other way is to use the gloves to provide the feedback to the pilot whenever he interacts with the simulation reality, right? So if he reaches a point that it's a solid surface in the simulation reality, then the glove will give the pilot the feeling that he's touching something. So he will be able to interact with a simulated cockpit graphics like that. Yes.
Where do you stand in terms of hardware at Auburn? Do you have a complete simulator, or I'm just kind of curious, do you still need some equipment?
Oh, so I'm going through the process of ordering the equipment. All the equipment have been chosen, and the equipment that I'm ordering is the one that they showed me in the simulation. But it will probably get at Auburn sometime in the summer. So I'm planning on to building and interfacing my software with the equipment throughout the summer and have the laboratory at least partially operative by start of the fall semester.
I look forward to seeing it.
Thank you.
Scott, I'll make a quick comment if I can. You mentioned data package, and yeah, that is the holy grail, really, especially for some of these unconventional configurations. So a lot of the projects we're working on, there is no data package. So we've also tried to put together a pipeline for generating the aerodynamic database that then goes into the simulator, because it doesn't exist as published lookup tables anywhere.
Yeah, on a $20 million simulator that CAA builds, it's probably $10 million will pay for the data package from Boeing. So the only alternative is to take an airplane and put a bunch of transducers on it and just download it.
Yeah.
One thing that perhaps I didn't mention is that I have other simulations models available that are based on a stitched architecture. So I basically take different linear models across the flight envelope and recreate a quasi-linear simulation that way. So if from an aircraft linear models or frequency sweeps were available such that I could identify the dynamics at a few different points across the envelope, then we could build a simulation that way as well.
Interesting. Thanks.
Okay, so I'm not sure if either Dr. Chakraborty or I have control now to stop the recording, because I think Dr. Thoreau went to the next session. So if there are no further questions, I'll stop the presentation. Okay, thank you, everybody.